Hello, and welcome to yet another video of Dr. Webb's. We are going to talk about the Kepler problem, which is a very important problem in classical mechanics. It falls in the general class of n-body problems, but so far only the two-body case has been exactly solved, and we'll see the exact solution this time for the special case of a captured orbit or planets, for example. Satisfy that. So I'll start by laying the groundwork for getting the Lagrangian, and from the Lagrangian symmetry, we'll conclude a couple of interesting things, which is the first part of Kepler's first law. I'll also talk a little bit about Kepler's second law. Then our main course for this video is the elliptic orbit solution, which proves actually the second part of the first law. Well, that takes care of the first and the second law, and the square cube law, the last one, we'll talk about at the end. So first of all, what are central forces and central potentials? These are forces or potentials that only depend on the separation between coordinates. So let's talk about that first. So if I have a potential V for two bodies, it's generally going to depend on the positions of the vector positions of the two bodies. But if that potential only depends on the magnitude of the vector difference, then that is called a central potential. So that it can be taken as the definition of a central potential. I'm going to invent a new vector known as the relative vector, which is the difference between the two vectors. And when I write r by itself without a vector sign, I mean it is the magnitude of the relative vector. So another way of writing the definition for central potential is that it is simply a function of r. Now when I write r hat, I simply mean the relative vector divided by its magnitude. So with that, let us write a couple of examples of central potentials. One example is Newton's gravity. So the force of gravity, Fg, is going to be negative Newton's gravitational constant times the product of the two masses divided by r squared times r hat, where r squared is the square of this and r hat is that. Another famous law is Hooke's law in 3 dimensions, and that is the force of a spring is negative k times r. So if you assume that the sun and the planets are connected by a spring, then this would describe the force of interaction between them. These are central forces, and the corresponding potentials can be immediately got. So the gravitational potential is just negative Gn m1 m2 over r, and the Hooke's law potential is just 1/2 kr squared. So these are the two relevant examples of central forces and central potentials. Now let us go to set up the Lagrangian. Our setup will involve two masses, m1 and m2. And there is some arbitrary origin, O, M1 makes a vector R1 with respect to O, and M2 is described by the position vector R2. The relative vector is the one joining M1 and M2, pointing towards M1. I'll explain why that is. And then I'm also going to write another vector, which is capital R, which describes the center of mass between the two objects. Now my drawing is such that M1 is more massive than M2. That's why the center of mass is closer to M1 than it is to M2. So that's our basic figure. Now let's try to understand why the relative vector looks like that. By simple vector addition, if I look at R1, I get it by adding R2 and R. So by simple vector addition, R2 plus R is the same as R1, which tells me that R is R1 minus R2 if I subtract R2 from both sides. And that is the reason why I wrote the R vector like that. It always points from the second object to the first object. Now the capital R, the location of the center of mass, is given by the usual formula for center of mass, and that is sigma mi divided by sigma mi, which is of course valid for any number of particles, not just two. So now let us apply that formula and see what we get. So that gives me R equals M1 R1 plus M2 R2 divided by the sum M1 plus M2. I'm going to also invent capital M, which is simply the sum of the two masses. Okay, now because of that, I can put capital M in the denominator and multiply through by capital M. So I'm going to get MR equals M1 R1 plus M2 R2. And here I'll use R2 equals R1 minus R. So I'll get M1 R1 plus M2 times R1 minus R. My purpose here is to find an expression for R1 and later an expression for R2 only in terms of the center of mass coordinate capital R and the relative coordinate little r. So let me proceed. Here I have a R1 and I have an R1 there. So that's going to give me M1 plus M2. R1 minus M2 times R. Well, that's just capital M R1 minus M2 times R. This I'm going to solve for R1 by taking M2R to the other side and dividing by capital M. So therefore, R1 equals capital R plus M2 over M little r. I'm going to save that equation. I'll just box it. And from that, you can find what R2 is. R2 is R1 minus R. So let me write that. And we already know what R1 is from that box expression. So that's just R plus M2 over M, R minus 1R. So that's M2 over M minus 1 times R. Let's simplify this. Remember that capital M is M1 plus M2. So if I take the common denominator, I'm going to get M2 minus M1 minus M2 divided by capital M times R. And so that's my second equation, R2 equals R minus M1 over M R. The way that some students like to remember this is R1, because the R vector is pointing from 2 to 1. R1 is capital R plus the other mass divided by the total mass times R, and R2 is the vector capital R minus the other mass divided by the total mass times R. But anyway, that's the expression. Now that we have R1 and R2 in terms of capital R and little r, we can sort of forget this origin. And now all our calculations will be in terms of the line joining the two objects and not an arbitrary origin. So the next step is to write the Lagrangian. So let's do that. Lagrangian L is the kinetic energy minus the potential energy. The kinetic energy is the kinetic energy of each object, and the potential energy is some central force, which I'm not going to assume anything about at this point. So we'll try to keep that, like to delay the form of the potential energy until it's absolutely necessary to do so, to proceed any further. So we'd like to see how general this problem is, known as the Kepler problem. So let's now figure out what the Lagrangian is. Well, the Lagrangian L is best written in terms of the original coordinates first, and then we'll simplify it to the new coordinates. So it's going to be 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared minus v as some function of r, where r1 dot squared is r1 dot dotted with r1 dot. So the square of a vector is the dot product of the vector with itself. Now r1 is just right here. When I take the dot, the masses don't get dotted because the masses are constant. If the masses change with time, then they also get dotted. So if you're talking about a comet, you've got to be careful. But as long as there's no mass loss involved, you just do the r dots there, the dots there, and don't worry about the mass. So I get r dot plus m2 over m r dot, and I dot that again with itself. Well, that's the sum of 4 terms. Let's write it out. The middle 2 terms are going to be identical because I'm going to get r dot m2 over m little r dot, and then I'll get that term again from here. So that becomes a 2. So I get r dot squared plus 2 m2 over m r dot dot r dot plus m2 squared over m squared r dot squared. Well, the only difference between r1 dot squared and r2 dot squared is that I have a minus sign here. That'll only affect the middle term. So I'll just straight away write that. This is r dot squared minus 2m1 over m r dot dot r dot plus m1 squared over m squared r dot squared. So now we are ready to write our Lagrangian. Therefore, the Lagrangian, which is now going to be a function purely of little r, capital R, little r dot, and capital R dot, and not a function of time. Well, what's that going to be? I'll just write everything out. 1/2 m1. And for r1 dot squared, I'll write this. Plus 1/2 m2. And for r2 dot squared, I'll write that. And then there's the potential term. Okay. You observe the middle term cancels out because there's an m1, m2. The 2 cancel out. m1, m2 over m. Here there's a negative m1 over m2 over m. So that cancels out. So I'm just left with 1/2 m1 plus m2, which is capital M, r dot squared. And here I have plus 1/2 m1 m2 squared, m2 m1 squared. So there's a m1 m2 that's common. If I take the m1 m2 common, I get an m2 extra from here and an m1 extra from there. So let me write that. And then I have r dot squared minus v of r. Well, m1 plus m2 is the same as capital M, so I lose one factor of capital M. And then I have this all-important quantity known as the reduced mass of the system. The reduced mass mu is m1, m2 over m1 plus m2. In a two-body problem, you always end up getting the reduced mass. The word reduced mass comes because the reduced mass satisfies the following equation. 1 over mu is 1 over m1 plus 1 over m2. In other words, it's the harmonic mean of the two masses. Whenever you have this situation, this is like adding resistors, for example, in parallel or capacitors in series. You always get this harmonic addition in those cases. It means that the reduced mass is less than the mass of the smallest mass. So if you have the Earth and the Sun, the reduced mass of the Earth-Sun system is actually smaller than the Earth's mass. So the smaller mass is what governs the motion, not the larger mass. So the reduced mass shows up in the relative Lagrangian, and the other Lagrangian has got the other chunk of the Lagrangian is the whole thing. So you can split up the Lagrangian into two parts. We'll call this the center of mass part, and we'll call that the relative Lagrangian. So that's our great achievement so far. We have been able to separate the Lagrangian. The Lagrangian L which is a function of those new coordinates, is now a function of the center of mass coordinates alone, and this is a function of r and r dot alone, and then a relative L-rel, which is a function only of little r and r dot. Of course, the LCM is just a kinetic term. There's no potential term associated with this. And the L-rel part has got both a kinetic and a potential. So let's write that down. 1/2 mu r dot squared minus v of r. I think it's a good idea to keep the vector hygiene important to do this, because soon we'll write this in terms of polar coordinates and it'll look a little different. Okay, so we have our Lagrangian. Well, immediately we can deduce the following. Since the Lagrangian is independent of the center of mass coordinates itself, it tells you that the momentum associated with the center of mass, which is del L over del R dot, or mr dot, is conserved. Which means that to study to the two-body problem or any planetary motion, you can remain in the center of mass frame. If you're stuck in the center of mass frame, you won't have to worry about the constant drift. For example, the solar system is drifting around the Milky Way galaxy. Well, it's not quite, linear momentum is not quite conserved because it's actually going around the central black hole of the galaxy. But for short distances, let's say a few years, when the Earth goes around the sun 3 or 4 times, the amount by which the solar system itself goes around the black hole is very negligible. So you can think of this as approximately conserved, at least, for our galaxy. So we're going to stay in that coordinate, we'll stay in that frame. Stay in center of mass frame. All right, so the relative Lagrangian is interesting because we basically have reduced the problem, the two-body problem, to a one-dimensional particle in a three-dimensional potential. So that's the beauty of this reduction. The two-body problem has now been reduced to a one-dimensional problem of a particle, and not one-dimensional problem. It's been reduced to a one-body problem where the body has got a mass mu. So it's a 1D particle in a 3D potential. Okay. Now the next thing is to write the Lagrangian in proper coordinates. So for this, we're going to go to the coordinate system known as the polar coordinate system. Now in the polar coordinate system, the r dot now in general, you can have spherical polar coordinates, but what I'm going to assume here is that all the motion happens in one plane. And the reason for the assumption, I'll tell you in a minute. But right now, let's proceed to do this, and then we'll talk about the assumption. The r dot vector becomes that in the r phi coordinate system. So this is an orbital plane. I haven't yet told you why the orbit is a plane. I'll tell you in a minute, but assume that you have that. Then if you square this, by square I mean dot products, and the dot product of ER and E phi are 0. So you're just going to end up getting two terms. So the LREL in the coordinate system r phi r dot phi dot is going to be 1/2 mu r dot squared plus r squared phi dot squared minus V of r. So we have succeeded in our first task, which is write the Lagrangian of the two-body problem. Now, why is it that I chose a planar polar coordinate system and not a spherical polar coordinate system? The reason for that has to do with angular momentum. Now, you can show, and this is a calculation I won't bother doing because I want to save some time. You can show that the total angular momentum, where L with a vector means angular momentum and not the Lagrangian, which by definition is R1 cross P1 plus R2 cross P2. When you substitute your P1 equals M1 times R1 dot and P2 equals M2 times R2 dot and carry out this enormous enormously messy thing, you will end up getting, and you're invited to verify this, the following simplified equation. It'll be 10 minutes more to the video if I showed it. And it's not that super exciting, so I'll just let you do it. So I'll get R cross PCM, where PCM is that, plus mu R cross R dot. This shows you that the total angular momentum splits up nicely into the angular momentum of the center of mass plus the angular momentum of the relative coordinates. Now, if you notice, this is independent of the angle, so the angular momentum is conserved by Noether's theorem. So the orbits will always be planar. So we're going to choose the orbit so that the relative angular momentum is along the z-axis. So I'm going to call the magnitude of the relative angular momentum, which is LZ naught, and not meaning it's constant. And I'll simply indicate that by curly L in future. So this is pretty much our first part of the first law of Kepler, which I'll call K1. Kepler's law is K. So this is K11. All orbits are planar. And K12 is going to be that all orbits are elliptical. Now that's going to take major effort to show. This was first shown by Newton. Newton, in fact, invented calculus to show this. All these great scientists of the past had a need to invent the mathematics in order to satisfy the physics of their time. So now let us draw roughly what the shape of the orbit would be. We don't know what it is, so I'll just draw a random orbit. And we have taken the z component of the angular momentum as our reference direction here. That's m2, and that's m1. And remember, your relative vector always points from 2 to 1, like that. And at any given time, it's going to subtend an angle phi. So that's our general state of affairs. Now we're going to prove Kepler's second law. We'll do the elliptical later. So Kepler's second law is the following. Equal areas are subtended by the relative vector in equal time intervals. The beauty of both K11 and K2 is they do not involve gravity. Why is that? Because I've not told you what V of R is. V of R could be gravity, it could be spring, it could be something else, it could be little green men. We don't know, all right? At this point, we don't know. So let's take the relative Lagrangian here and investigate something about it. We notice that the rate of change of the relative Lagrangian with respect to phi is 0 because there is no phi coordinate in there, which means that the corresponding canonical momentum, which is del L rel over del phi dot, and that is simply mu times r squared phi dot, has to be constant. And that's what I told you is our L. Okay, so we have a formula for the angular momentum, z component of the angular momentum in this fashion. So what we're going to do now is solve for phi dot. So phi dot is going to be equal to L over mu r squared. Well, that's a really important equation because it's an equation that connects the angular speed of the orbit with the size of the orbit at any given time. Now, one more step. I'll write the relative Lagrangian later, but right now I want to prove Kepler's third law. The proof is actually kind of neat. I can use this figure. So if I imagine that I'm going for a short distance, then this is going to be delta phi. Let's say I go from r to r prime. Some new location in that short time. Now this orbit, we don't know what shape it is. So we cannot make any statement about the shape. It could be an ellipse, for example. But in that short period, delta S would be a continuation of that. All right. And so delta R, which is the completion of this triangle, would look like this. So in that small interval, you can assume that to be a right angle triangle. Now let's write down a couple of things to prove Kepler's second law. Proof of K2. The proof of K2 goes like this. The area, because K2 is about areas, what is this area we're talking about? It's this area. Okay, it's the pi slice. Well, that area, which we'll call delta A, is going to be half the area of the parallelogram, and the area of a parallelogram is the cross product of the two vectors r and delta r. Well, the geometric meaning of the cross product is that it's the magnitude of the one times the magnitude of the other times the sine of the angle between the two. The angle between the two is this angle actually, because r and delta r. So I'll call this delta psi. Okay, so this is going to be half the magnitude of r times the magnitude of delta r times sine psi. Well, the magnitude of r is just little r, relative vector's magnitude. Delta r sine psi is just delta s. So I'm going to get r times delta s. Okay, now delta s, however, is r times delta phi. So I have this incredible result. It's 1/2 r squared delta phi. Those who thought this was heavy-handed can simply remember the polar coordinate formula for the area of a circle, area of the sector of a circle. It's just 1/2 r squared phi, and take the infinitesimal version thereof. So you can also do it like that. Now I'll take everything, all this is happening over a small time interval delta t, so I'll divide by delta t, and so I'm going to get 1/2 r squared delta phi over delta t. And now I'll take the limit as delta t goes to 0. Well, when you do that, the limits apply to the whole thing. So I'm going to get dA by dt, which is a dot, is 1/2 r squared d phi by dt, which is phi dot. Meanwhile, phi dot is that. So I get a dot equals 1/2 r squared L over mu r squared. A miracle happens. The r squared cancels out. You know, look at this. Look at how beautiful the universe is. R squared cancels out, and I get L over 2 mu. Well, L is the z component of the angular momentum, which is constant, and mu is the sum of reduced mass, and that's also constant. So this is constant. And we have proved Kepler's second law. The rate of change of area is a constant. So the important takeaway from this is that we do not need gravity. Gravity not needed for the first part of Kepler's law that states that all planets move around stars in one plane, known as the plane of the ecliptic in our solar system. So gravity is not needed for that, and gravity is not needed for K2 either. Gravity is only needed for K3 and the second part of K1, which says that all orbits that are trapped are elliptical in nature. So that's going to be our next focus. We're going to take this relative Lagrangian and work with it to get ellipses. So that's going to take us a while to do because it's somewhat involved. So let us now continue with the relative Lagrangian, which I wrote here. L-rel is equal to 1/2 mu. And what I'll do now is I will substitute for phi dot because I know that the phi dot term is given by this. So that's an important equation. I'll box it. I'll put this in there. So I get 1/2 mu r dot squared plus r squared little l squared over mu squared r to the 4 minus v of r. So I simplify this. One of the factors of r squared and r to the 4 cancel out. So I'm going to get 1/2 mu r dot squared plus l squared over mu squared r squared minus v. We are now in a position to write the equation in the r direction. In the r direction, we don't have any symmetries because the Lagrangian does depend on r. So we have to just bite the bullet there and write it down. I'll call the Lagrangian just L. So I'm going to get del L over del R minus d by dt of del L over del R dot is equal to 0. Or I could have done minus and plus. It doesn't really matter. Let me do minus and plus. So del L by del R dot is just mu R dot. When I take another derivative, I get mu R double dot. So I'm going to get mu R double dot. And then negative del L over del R. If I take del L over del 1 over r squared, I'm going to get a negative sign. But because of that negative sign, that's going to become a positive sign. So let's see. Carry out this computation. Well, I think I'm going to do the following. Rather than do the R equation, let me proceed straight to energy. The energy is got by taking the Lagrangian, the kinetic energy term, and adding it to the potential energy term. So I'm going to do that. So this is total energy is conserved. So that's 1/2 mu r dot squared. I'll multiply the mu inside plus 1/2 mu r squared phi dot squared. I'm going to write in terms of phi dot squared instead of L squared plus V of R. If I want to write it in terms of L squared, I'm going to get 1/2 mu R dot squared plus 1/2 L squared over mu R squared plus V of R. The energy approach is easier to use because you get immediately the notion of an effective potential. V effective. The effective potential is a sum of two terms. It's a sum of the actual potential, external potential, and the potential known as the centrifugal potential. By the way, the energy is conserved because the Lagrangian is independent of time. So that's how you get the conservation of energy. Now, let's spend some time plotting this thing here. Now, in the back of my mind, I know that central force is for gravity, so I'll keep that in mind, which means that V itself is negative. So for gravity, this is going to take the form V is going to be equal to negative some constant K over R squared. No, just R. K over R squared is the force. K over R is the potential. So that's for the potential for gravity, where K is G Newton M1 M2. Now, because of that, I know that at large positive values, that's going to go to 0 from below. For small values, it's going to go like this. So if I were to plot just the 1 over R, it would do this. And then I have the centrifugal potential, which is 1 over R squared. So when R is very big, it goes to 0 from above. And when R is really small, it goes to infinity like this. So this one, choosing a different color, will do that. When I put those two together, the thing that will win is still 1 over R squared compared to 1 over R. So the effective potential is going to look like this for gravity. So just looking at this picture, we can actually see all the features of the two-body problem come out immediately. You have a special place here, a single unique value of R, where the orbit remains fixed distance. That's the circular orbit. If the orbit shuttles between 2 points, such as this point, let's say that's the minimum energy needed. The energy is the smallest possible energy. The energy is slightly bigger than that. Let's call it E prime. Then the orbit has got two places, a minimum and a maximum place. The minimum is usually called a perihelion, and the maximum is called an aphelion. All right, that's the term for solar system. And these are elliptical orbits. Then there's a special orbit where the energy is exactly 0. When energy is exactly 0, total energy is exactly 0, the kinetic and potential balance out, and the particle comes very close to the sun, and then it never comes back. That's the first escape of the escape orbits. So that would be escape along a parabola. So that's parabolic escape. If the energy is positive, then of course, you're going to rebound with a great speed, and at infinity also you're going to be moving, and that's called hyperbolic escape. So this is the reason I like to work with energy. You can see all the features of the Kepler problem immediately. All right, now let's use the energy to write down the shape of the orbit. So what I want to do now is to get the orbit's shape. I can get the shape either as phi as a function of r, or r as a function of phi. So you have two options for orbit shape. So I'm now trying to move towards the great proof of ellipse that Newton gave. Let's choose r as a function of phi. Let us call the quantity s dr by dt. Well, that is dr by d phi times d phi by dt. By the chain rule. Well, d phi by dt, also known as phi dot, is our conserved angular momentum, which is right here. So let's write that down. In fact, I'll write d phi by dt first. So that's L over mu r squared times the other thing, which is dr by d phi. So let us write the energy, total energy of the orbit, r dot is S. So E equals 1/2 mu, all of that, squared. So that's going to be L squared over mu squared r squared, oops, mu squared out of the 4 times dr by d phi, the whole thing squared, plus the centrifugal term, plus v of r. Now, there's an r to the power 4 term here. There's an L squared over 2 mu. One of these mu factors cancels out, and I get L squared over 2 mu in both terms. So I can rearrange this as follows. I can write this as 1 over r to the 4 dr by d phi, the whole thing squared, plus 1 over r squared, and I can strip L squared over 2 mu and transfer it to the other side. So that gives me 2 mu over L squared v of r minus E equals 0. So this might seem like not a big deal. All I've done is played around with the energy equation to get something that looks even more complicated. But now there's a magnificent trick that either Newton or Kepler, I'm not sure who, discovered. And probably Newton, because Kepler did not know calculus. Let U equals 1 over R. Then du by d phi, what is that by chain rule? By chain rule, the rate of change of u with respect to phi, because u is 1 over r, that's going to be negative 1 over r squared times dr by d phi. Well, 1 over r squared is negative u squared dr by d phi. Therefore, I found out what dr by d phi is. Dr by d phi is none other than negative 1 over u squared. I take this to the other side, du by d phi. And now I can put this back in here. So therefore, this equation, 1 over r to the 4 becomes u to the 4. And then for dr by d phi squared, I'm going to write that. When I square, the negative sign does not matter. So that gives me 1 over u to the 4 du by d phi squared. Observe that these two cancel out, plus u squared, because 1 over r squared becomes u squared. And then here, there's nothing going on except that v has become a function of 1 over u instead of r. This important equation I'm going to call equation star. We'll come back to equation star soon. So we're going to use equation star. So I'm going to make some assumptions about the potential. So far, I've assumed nothing about the potential. Well, I kind of assumed something about it to draw the cute picture, but now I'm going to assume nothing about it except that the potential V is bigger than or equal to 0 and increases monotonically with decreasing r. Well, the only reason I do that is because then it'll make sense to put this under the square root. So we have a minimum radius, which I indicated by r minus. So the potential at the minimum amount, it's not moving there. So the total energy will not have this term at all because it's not moving at the minimum point. So I'm going to have V of r minus plus L squared, looking at this equation here, plus L squared over 2 mu r minus squared equals E. So that is a good equation to have. Now, meanwhile, I can actually solve for this. So let me solve for du by d phi. So du by d phi, because of the square, I have that equal to plus or minus the square root of everything else. That is not du by d phi. So that's going to be 2 mu over L squared E minus V of 1 over U minus U squared. And that can be immediately integrated. I get phi minus phi naught equals plus or minus the integral from this smallest value of U to the full value of 2 mu over L squared E minus V of 1 over U minus U squared to the power minus half du. This important quantity is called the true anomaly. The true anomaly is the angle made by the relative radius vector from the planet to some reference angle phi naught. Astronomers call this the true anomaly. Now, the other thing you can do is you can stick with the dr by d phi, dr by dt formulation of energy, which is here, and write dr by dt. You can solve for dr by dt. So I'll do that also because I want to introduce another term. So dr by dt is going to be equal to plus or minus square root. I'll transfer everything over to the other side. So that's going to be 2 over mu E minus V of r minus L squared over mu squared r squared. And then when I find out the time, t minus t naught, that gives you the orbital time, plus or minus r naught to r, 2 over mu E minus V of r minus L squared over mu squared r squared to the power minus half dr. This is called the mean anomaly. It basically solves the time as a function of the relative radius position. So these are important moments in orbital theory, which I'm highlighting. But that's not, my main reason is not show and tell. I actually want to solve for the orbit. So let me go back to equation star, which is this. So we'll go back to equation star and actually solve. So let me rewrite equation star here. Du by d phi, the whole thing squared, plus u squared plus 2 mu over L squared V of 1 over U minus E is equal to 0. What I'm now going to do is I'm going to take d by dt of both sides, d by d phi of both sides. So I'm going to do d by d phi of equation star, which this is equation star. Well, if I take d by d phi of that, I'm going to get 2 du by d phi times d by d phi of du by d phi, which is d2u over d phi squared. Now for u squared, I'm going to get 2u du by d phi. And then here, the E term, because energy is constant, will not contribute. So I'm going to just get 2 mu over L squared dV by du times du by d phi equals 0. Now you may wonder, what is this? This looks even worse than equation star. But actually, it's a better equation because du by d phi is now common to all these terms. So I can take out du by d phi altogether. Well, when I take out, what I really mean is there are two solutions. You either have du by d phi equal to 0 or not, or the rest of it equal to 0. The two factor can be cancelled out. So I get d2u over d phi squared plus u plus mu over L squared dv over du equal to 0. So these are the two possibilities. Du over d phi equal to 0 means that u is constant. And if u is constant, it means r is constant. That is your famous circular orbit. That's lowest energy case. Okay, so we've recovered the circular orbit case. But wait, we have still not assumed anything about the potential. So what we have essentially shown is circular orbits always exist. Whether or not the potential looks like gravity or spring or little green men, circular orbits will always exist. So that's a pretty outstanding conclusion, just like that. Now, we're now going to talk about the Coulomb-Kepler problem. So this is the first time in this entire video, almost an hour in, that I'm actually assuming anything about the potential. The potential will be taken to be K over R, which is K times U. And we're also going to assume that K will be less than 0. So I'm changing my convention a little bit from the way I drew my drawing. My drawing assumed the potential is equal to negative K over R, where K was equal to Gn M1 M2. Now I'm going to assume the potential equals K over R with K less than 0, which means that K will be negative Gn M1 M2. Slight change in convention just to make things look different. So dV by du, which we need to do this, is simply K. Let us solve this equation. Going back here, I'm going to get d2u over d phi squared plus u plus k mu, because dv by du is simply k mu over L squared equal to 0. Now that is a beautiful equation. It's actually very simple to solve. So we'll solve it in two stages. The first stage is the free potential case. Suppose you switch off K. It's an on-off switch, and you switch off K. K is equal to 0. So then I'm going to get d2u over d phi squared plus u equal to 0. Well, that's just a standard simple harmonic equation, except not in time. It's an equation in phi. So you can immediately write the solution from knowing your basic physics or basic mathematics as that. Now, if you remember that u is 1 over r, this immediately tells you that 1 over r equals 1 over r naught cosine phi minus phi naught, which can be written as r naught equals r cosine phi minus phi naught. Let's try to interpret this result in the two-dimensional plane known as the polar coordinate plane. In the polar coordinate plane, I'm drawing the Cartesian even as I speak because it's easier to visualize things in Cartesian. But in the polar coordinate plane, all you're allowed to draw is this r vector and the theta, or the phi angle. So this total angle phi from the initial ray. Phi naught is some reference angle. And at that angle, the value of this is r naught. So the nature of the orbit is such that r cosine phi minus phi naught, which is this angle, r cosine phi minus phi naught is precisely r naught. So we have proved that the orbit is a straight line. Well, that makes sense. If you switch off, if you cut the cord of gravity between the Earth and the Sun, the Earth would shoot off in a straight line. So this is a beautiful solution to the extreme case of the gravity being turned off. If the potential is not free, you'll just have an additional term. So that solution is known as a displaced harmonic oscillator. K not equal to 0 is called a displaced harmonic oscillator. And the solution, as you can readily verify, you just have to add the particular solution to it. So the solution is u equals u naught, same as the free particle, except you add the particular solution, k mu over L squared. Let's verify it. When I differentiate this 2 times, I lose that, plus u, which has got negative k mu over L squared, plus k mu over L squared is equal to 0. Indeed, it works. Now, what I'm going to do is I'm going to use this in the equation star. So let me get back the original form of star, which is here. So I'm going to put this in the equation star, even before. Let me rewrite star in a slightly different way. So I'm going to rewrite this as follows. E is equal to, V is just Ku. Well, V is Ku. I'll move this 2 mu over L squared back. So that's going to be L squared over 2 mu, attacking this time du by d phi squared plus u squared. And now I have the V exposed all by itself, but V is Ku. So I've used equation star to write energy like that. I want an expression now for the total energy, because that's important. Well, since my solution of the displaced harmonic oscillator is right there, let me write down what that is. U equals u naught cosine phi minus phi naught minus k mu over L squared. And now I'll differentiate because I need du by d phi. So du by d phi is negative u naught sine phi minus phi naught. And I'll simply substitute it into this equation above. So I'm going to get E equals L squared over 2 mu. The negative sign does not matter when I square. And u squared. U squared will be a sum of 3 terms. So the first term is u naught squared cosine squared. The second term will be the mixture of the two with a 2 factor of 2. So that's negative 2k mu over L squared u naught cosine phi minus phi naught. And the last term will be that thing squared. So that's k squared mu squared over L to the 4. k. Then plus k times u. So I'm going to get plus k times u naught cosine phi minus phi naught minus k squared mu over L squared. Observe that this term and this term cancel out because L squared over 2 mu leaves you with negative of this. So we have a beautiful cancellation. Sine squared plus cosine squared is 1. So our expression drastically simplifies. L squared u naught squared over 2 mu minus just this term here. What we have is k squared mu squared divided by mu. So that's k squared mu over 2L squared, because L squared and L to the 4 cancel out, minus k squared mu over L squared. So that gives me k squared mu over 2L squared. 1 minus half is half. It is now that we make the assumption that k is less than 0, which is true, then, so that's the energy, the particle. If k is less than 0, we can write the equation for u as follows. 1 over r, which is the same as u, this one. I'm going to write it in the following way. I'm going to take k mu over L squared outside. Actually, I'm going to take negative k mu over L squared outside. Then I just have 1 from that. And this one I have to repair. And the repair is just put the reciprocal of what you took outside. Okay. All right. So we're getting close to the solution that Newton gave. Newton defined the following quantity known as the eccentricity. He called epsilon, which is negative u naught L squared over k mu. Remember that k is negative, so epsilon will actually be positive. The eccentricity. With that definition, I'm going to get 1 over r equals negative k mu over L squared times 1 plus epsilon cosine phi minus phi naught. I can rewrite this as by taking r there and everything else here. So I'm going to get r plus epsilon r cosine phi minus phi naught equals negative L squared over k mu. Can you look at that and say that it's an ellipse? I cannot. So we have to do more honest labor. And that honest labor is going to take the form of squaring both sides. But if I square now, I'll end up in trouble. So what I'll do is I'll take this to the right side and then square. So I'm going to get r equals negative L squared over k mu minus epsilon r cosine phi minus phi naught. And now I'll square. So r squared is equal to L to the 4. When I square, the negative signs will disappear. So this is just k squared mu squared plus 2L squared epsilon over k mu r cosine phi minus phi naught plus epsilon r squared cosine squared phi minus phi naught. At this point, let's use the meaning of polar coordinates. So x is r cosine phi minus phi naught. Y is r sine phi minus phi naught. Well, r squared is x squared plus y squared. So I have my equation looks like x squared plus y squared equals L to the 4 over k squared mu squared plus 2l squared over k mu epsilon x, because r cosine theta is x, plus epsilon squared x squared. Still doesn't look totally convincing to me as an ellipse, so I'll take this epsilon squared x squared to the left side. So I have 1 minus epsilon squared x squared. I'll move all the x terms to the left side. 2l squared over k mu epsilon x plus y squared is equal to L to the 4 over k squared mu squared. Well, what to do with this? Well, what we're going to do with this is to write it by completing the square. So these are old tricks you learned in high school or something, and we're using it in graduate work. So it goes to show that you never not need simple math. So the way you complete the square is to take the 1 minus epsilon squared outside. Right. Then I have x squared minus 2l squared over k mu epsilon over k mu 1 minus epsilon squared x. And then when you complete the square, you have to add and subtract the same term. And that term is going to be b squared. So, oops, L to the 4 epsilon squared over k squared mu squared 1 minus epsilon squared whole squared. And when I subtract the term, I'll have subtracted with this 1 minus epsilon squared multiplying it, so that square part goes away. So I'm going to get negative L to the 4 epsilon squared over k squared mu squared, just 1 minus epsilon squared because of that cancellation with the square, plus y squared equals the right-hand side, L to the 4 over k squared mu squared. Beautiful. So this is 1 minus epsilon squared, and we have completed the square, so that's x minus L squared epsilon over k mu 1 minus epsilon squared plus y squared equals, I'll move this to the other side. I have L to the 4 over k squared mu squared common, and then I have 1 plus epsilon squared over 1 minus epsilon squared. Well, this is just 1 minus epsilon squared plus epsilon squared is just 1. So this is just L squared over k squared mu squared 1 minus epsilon squared. So this is an ellipse. It's a displaced ellipse. So now we're going to take the eccentricity to be, this actually contains all the cases. For epsilon equal to 1, it's the parabola. For epsilon bigger than 1, it's the hyperbola. So all the cases are contained here. We're going to take only this case for this video. This is a famous case of ellipse. And that's what really concerns us, because all the planets are trapped in elliptical orbits around their stars. So for that particular construction, the quantity A, known as the semi-major axis, is defined as follows. And there's a quantity B, the semi-minor axis, that's L squared over k mu square root of 1 minus epsilon squared, which by the definition of A is just going to be the square root of 1 minus epsilon squared times A. Under these conditions, we can, I'll pretty soon draw the ellipse, but I want to write the equation first. We have the famous solution of Newton to the Kepler problem. X plus epsilon A squared over A squared. Now if I bring this down, it's going to look a lot like A squared. With this 1 minus epsilon factor taken down, okay? And it looks like A squared. And then I have plus y squared over B squared equals 1. Now that, you cannot argue, is the equation of an ellipse. Let's draw it. this ellipse is very simply drawn. That should be displaced a little bit. So the center of the ellipse, if you wish, is going to be that. The semi-minor axis is that, and the semi-major axis is this. The distance of the sun from the center is this quantity epsilon a. So if epsilon is 0, that'll become a circular orbit. If epsilon is not 0, it's going to have this little displacement. If epsilon is really elongated, then it's close to 1, very elongated line segment-like orbit, then it'll take up all of the space. So this is the position of the sun, marked S. The planet will be here, marked P. So we have our beautiful solution to the Kepler problem. A is known as the semi-major axis, and B is called the semi-minor axis. All right, what else can we do with this thing? A couple things. We can show the energy is less than 0, so the particle is always trapped. That's the important thing. You don't want the planet shooting off to infinity. The other thing you can show is we can try to prove Kepler's third law. So let's try both in the remaining time. Okay. So first of all, the equation for the ellipse, by the way, can be written now in terms of A and B. I'll leave that as an exercise for you as follows. So that's our Keplerian ellipse. When phi equals phi naught, you're said to be in perihelion. When you put phi equals phi naught, cosine becomes cosine of 0 or 1. So this radius of perihelion is just 1 minus epsilon squared over 1 plus epsilon, which is 1 minus epsilon times A. When phi equals phi naught plus pi, you have what's called the aphelion, the farthest distance. Well, what is the farthest distance? When you put phi naught plus pi, you're going to get 1 minus epsilon. Well, 1 minus epsilon squared over 1 minus epsilon is 1 plus epsilon, so that our aphelion is 1 plus epsilon times A. And so the average distance is the semi-major axis, because if you take the perihelion and the aphelion and average them, you get the semi-major axis of the ellipse. Okay, so that's an interesting feature. The total energy next. We have to prove the total energy is less than 0, so the particle doesn't escape. So let's remember the definition of eccentricity. From that, we get here. From that, I'm going to get U naught equals epsilon times k mu over L squared. Okay, let's use that. The energy, total energy of the particle is right here. The total energy E equals L squared U naught over U naught squared, excuse me, over 2 mu minus k squared mu over 2L squared. So I'm going to substitute what I have in there. So that gives me L squared epsilon squared k squared mu squared over 2 mu L to the 4 minus k squared mu over 2L squared. One factor of L squared, I get a factor of mu. So this is identical to that. So this is just negative 1 minus epsilon squared k squared mu over 2L squared. Now at this point, I want to substitute what the orbital parameter A is. A is negative L squared k over mu, k mu over 1 minus epsilon squared. So this is going to be k over 2a. And because k is less than 0, we have the energy is less than 0. So the orbits are stably bound. I'm waffling a little bit because I've really not shown you stability. In a subsequent video, we'll address stability, but we have shown that important result. Last thing is the third law of Kepler. Third law of Kepler is only valid for gravity. What is the third law of Kepler? Let's state it. The third law is sometimes called the square cubed law. Actually, rather than state it, I'll simply prove it for you. The important thing is once you have the ellipse, the area of the ellipse can be easily found. The ellipse area, which you can look up in any Wikipedia or someplace like that, or actually prove it to calculus, the ellipse area A is just pi AB. If A is equal to B, then it's pi r squared, the usual formula for a circle. Now, earlier in Kepler's second law, we showed the rate of change of area was fixed. Let me see if I can find that sheet. I have this here, K2, L over mu r squared. But A dot, the rate of change of area and the proof of that, there it is. Proof of K2, here it is. A dot is L over 2 mu. So let's grab that. It's L over 2 mu. Well, the orbital time, the time taken to orbit is just the area divided by the rate of change of area. That's no doubt about that. So that's just pi AB over L over 2 mu, which is 2 pi AB mu over L. Let's do the square of the period because the third law concerns the square. So that's 4 pi squared, A squared, B squared, mu squared over L squared. Now, L squared is actually given in terms of A. It's right here. So let me write that immediately. L squared is negative K mu A 1 minus epsilon squared. And B squared is the square of this. So that's going to be 1 minus epsilon squared A squared. I'm going to substitute it here. So I'll get 4 pi squared A squared 1 minus epsilon squared. I'm substituting for B squared now. And for L squared, I'm going to substitute negative K mu A 1 minus epsilon squared. Lo and behold, I lose 1 minus epsilon squared. I also lose a factor of A. A factor of mu goes away. So let's see what I have. Now at this point, I'm going to stick in what negative K is. Negative K is G Newton M1 M2. So this is going to be 4 pi squared A cubed mu, which is M1 M2 over M1 plus M2 divided by negative K, which is G Newton M1 M2. The M1 M2s cancel out, and so I have the famous third law of Kepler. The period of the orbit squared is 4 pi squared over G times the capital M, the total mass, A cubed. This law has been very useful in our understanding of the universe because It is using this law that the mass of distant stars have been determined. Little a you can get by looking at stuff. Tau you can get by looking at your watch. It is capital M that's the big mystery, and that can be found.